Hello everyone, I'm Shuo from the National University of Singapore. Today, I would like to present to you our recent work on motion planning. FISS, a trajectory planning framework using fast iterative search and sampling strategy for autonomous driving. In recent years, low-speed autonomous applications such as delivery, patrolling, and road sweeping vehicles start to emerge. Due to the size and power constraints, autonomous vehicles of these applications are often equipped with lower-spec computers. Meanwhile, as the safety and functional requirements for these applications become increasingly complicated, the onboard computers are burdened by many software modules, leaving very limited computational resources for the planning module. In this context, many trajectory planning algorithms could not meet the real-time requirement and thus cannot be deployed in these applications. There's a need for more efficient planning algorithms to enable more autonomous robot applications. Sampling-based trajectory planning algorithms are widely used in autonomous applications for its simplicity and effectiveness. This type of algorithms usually samples a large number of candidate trajectories in the spatial temporal space, and chooses the best candidate that satisfies all the constraints with the lowest cost. In conventional frameworks, all trajectory samples are generated and evaluated together as one batch, which is redundant and computationally heavy. We propose a general planning framework using a fast iterative search and sampling strategy, which is able to prioritize those candidates that are more likely to become the optimal solution and avoid exhaustive generation of all candidate trajectories to improve the overall planning efficiency. In our framework, we only sample the end states and estimate the real cost distribution on the sampling space before actually generating any trajectory samples. In this way, trajectory candidates can be pre-ranked according to their estimated costs and evaluated one by one during the iterative search and sampling process. The process will go on until an optimal candidate has been found. If this candidate violates any of the safety constraints, a new search will start on the remaining of the sampling space until a feasible trajectory has been found, or all samples have been explored. This process can guarantee a solution when one exists, and it can guarantee that the final output trajectory satisfies all the safety constraints. Before each search iteration starts, we use a heuristic function based on the historical planning results to provide a close initial guess to accelerate the search process. And at every search step, our method will generate one trajectory sample with its neighbors and compute the local cost gradient. Then, by using the gradient descent method, our algorithm is able to gradually converge towards an optimum without actually generating most of the other trajectory samples. We conducted a series of experiments in the simulation environment to benchmark the performance of our method and the baseline methods. Experiment results shows that our framework can significantly reduce the number of trajectories generated compared to the two baseline methods, and achieves about 9 to 24 times improvement in planning speed, while maintaining an accuracy of about 93 to 96%. By plotting the relationship between the total number of trajectory samples and the algorithm's average execution time at a log scale, our method demonstrates a trend of O log n, and is proved to be faster than the conventional framework by an order of magnitude. Furthermore, it is worth highlighting that the design of our framework guarantees that the final output trajectory is safe, with no safety constraints violated. We also conducted a real-world experiment using an autonomous road sweeper which has lower computational power to demonstrate the effectiveness of our proposed method. Here's a video showing our algorithm in action on our campus. In the video, the blue waypoints in front of our vehicle represent the trajectory that our vehicle is currently executing, and the curves with different colors are the future trajectory samples with different costs, with red representing the highest cost. The green boundary shows the vehicle footprint being projected forward based on the current motion. At this moment, our algorithm receives information about a fast-moving obstacle in our lane, and finds that all trajectory samples are not safe. Thus, it guides our vehicle to come to a brief stop and then continue its mission after the obstacle moves away. And now, our planner finds that the left half of the sampling space is entirely occupied by multiple static obstacles, while the right-hand side is still viable. Thus, it chooses a sample slightly on the right and steers our vehicle to navigate through. In summary, our method achieves a significant improvement of about an order of magnitude in execution time compared to the existing frameworks, while ensuring safety and maintaining high planning accuracy. This provides a great opportunity for applications with limited computational resources that are willing to trade a small amount of optimality for a vast improvement in planning efficiency. Thank you all for watching. If you're interested in our work, please do check out our paper and the open source code in the links below. Have a good day.